So hello, welcome back to another Mathcounts meeting. Today we're gonna finish 2016 nationals, hopefully, and yeah. So we were on target. All right. So yeah, so we did this one, right? And I don't think we've done this one yet. So yeah, for the integer data set, 11, 13, 15, 17, x, y, the unique mode, median, and mean form an increasing arithmetic sequence in that order. What is the greatest possible value of y? And so x and y in that set, it like that whole set isn't arranged in an increasing sequence already, right? Like I'm saying, x and y don't have to be greater than 17. X and y can be like anywhere. They just put it at the end of the set. So yeah. So the mode, median, and mean form an increasing arithmetic sequence, and we want to find the greatest possible value of y. All right. Um, so maybe we should look at the mode first because that's kind of like I don't know, easy to think about. So there's a unique mode, right? Which means what? Which means like the greatest number of so the mode is like the number that occurs the most, right? And if there's a unique mode, it means that number of times that number occurs, there's no other number that doesn't occur as much as that number, right? Right, which means that x or y have to equal one of the 11 through 17 numbers, right? But they can't both equal like different ones. So yeah, okay. And let's think about the median. The median will be one of the numbers, one of the four numbers that were given, right? There's no way that x and y can like totally skew the median like out of this range, right? That makes sense because we only have like x and y are only two numbers and we have four given numbers, right? So we know the median is somewhere in here, right? And we want to maximize the mean, right? Because we want the greatest possible value of y that's most likely going to occur with the greatest mean that we can get, right? So we want to get the greatest possible mean. The median is like pretty much fixed. So what does that mean? That means we want to try to minimize the mode, right? Because they form an increasing arithmetic sequence, if we minimize the mode, we can get the greatest mean that we can get, right? All right, so we want to minimize the mode, right? So we can do that by making the mode 11. Now we can get a smaller mode like I don't know, 9 for instance, but if we were to do that, we would have to set x and y both equal to 9, right? And that would be bad because y is a really small number. So we don't want to do that, right? So we should just make the mode 11 with x equaling 11, and then we have y to be whatever, right? We don't want y to be 11 because we want to maximize y, right? Okay, so we should try x equals 11. So that would make the mode 11, right? Okay, so the mode will be 11, and then we can think about the median now, right? So we're going to have 11, 11, 13, 15, 17, and y, right? And we I don't know, we can just assume y to be greater than 17 for now and see if it works out. Yeah, so if we do that, then the median will be 14. And then so we try this out, and then the because this forms an increasing arithmetic sequence, the mean will be 17, right? And then we should see what y will equal if the mean is 17. So you could just do it by like you know, using the formula by summing all of these numbers, dividing it by 6, and setting it equal to the mean, which is 17. But I have a cooler and faster way to do it. So basically, it looks at the differences of each of the numbers to this number. So basically, like 11 is 6 below 17, right? So I could write a -6 on that, and then 11, there's another 11, so I can write another 6. 13 is 4 below 7, so I can write a -4, and then 15 is 2 below 17, right? And then 17 is 0 below 17. So if we look at all of that, then all of that, the total of that being below 17 is what is 18 below 17, which means for y to balance everything out with mean 17, y will have to be 18 greater than 17. Yeah, so y will have to be 18 greater than 17, so y will then have to equal 35. And we assumed y was greater than 17 when we calculated our median, right? So, and that still works out, right? So this should be our answer. Yeah, 35 is our answer. Okay, cool. Not too bad. Number 4 in Pentagon ABCDE shown here. Angle EAB is 60 degrees. Maybe let me try to zoom out a little bit. Okay. Angle EAB is 60 degrees. All other interior angles of the pentagon measure 120 degrees. If AB and AE is 2 units and all of those sides are 1 unit, what is the ratio of the area of triangle ACD to the area of the pentagon ABCD? Okay, so what we could do here is we could try to find the area of the triangle and find the area of the pentagon and then just put it in a ratio. So we can try to find this height of the triangle because, we already have that base right there. So let me draw a rough picture if I can. It's going to be like this. All right, and then have DCBA and E right here. All right. And we have a triangle right here. All right, and these are 2, 2, 1, 1, 1. Okay.
Shan is saying you can't do that in the real test.
Wait, what?
Shan is saying you can't do that in the real test.
Can't do what?
He just said you can't do that.
Can't do what?
Oh wait, hang on. Were you having a conversation with 1001? Oh, the copying the thing. Okay. Oh, I mean, like,
Oh, well, I
by
mean,
copying the thing, we basically what we're actually doing is like, if you were on the test, what you actually be doing is just drawing the
yeah,
diagram
on the
itself.
test you have the diagram like in front of you, right? So
Yeah.
you can copy it.
Yeah. In this case, we're just copying
Um,
onto here so we can draw on it.
yeah, I don't know. Sure, yeah, you can copy it, or I can copy it, but I don't know. I'm practicing my drawing skills. I don't know. I can also copy it if you guys want me to. Yeah. Okay. Um, okay, so we can try to find the height of the triangle, right? So what we could do is we could draw a line right here, and this line would separate so this angle is 120 degrees, right? This line is going to separate the angle into 60 degrees and 60 degrees. And then whoops, okay. And then we can draw like 3 equilateral triangles right here. And these will all have sides 1. And this is also an equilateral triangle, right? Because this angle is 60 degrees. So then this side would have to be 2, right? And that makes sense because we separate it into the 3 equilateral triangles, and it also says it has a side length of 2. Um, so yeah, if we do this, then we can just get like this height of the yeah, okay, we can just get this height of this equilateral triangle and this height of this equilateral triangle and add them together to get the full height of this triangle, right? So so yeah. So in this equilateral triangle, we have sides of 1, right? And to get the height, we could just drop the height down like that. And we know this is 90 degrees, we know this is 60 degrees, and this is 30 degrees, and this will be 1/2, right? So this is going to be √3/2, and you can just memorize that, right? And then the scaled up version by 2 in the bigger equilateral triangle, it's just the height is just going to be this height times 2, right? So then our full height will be √3/2 plus √3, which is 3 times √3/2. Okay, and then the area of the triangle will just be 1/2 times 3√3/2 times 1, which is just 3√3/2. Or sorry, what? 3 times √3/4. Okay, and then we can just find the area of the pentagon, and we'll have our answer. And finding the area of the pentagon is not bad as well because we drew it all in equilateral triangles, right? So so to find the area of the equilateral triangle, you can just like do this, right? And you have the height, you have the base, you can get the areas like that. But there's also actually a formula for the area of the equilateral triangle, which may save you a little bit of time. It's that the area of an equilateral triangle with side s is √3 times s squared over 4. Okay, so then the area of our pentagon will be 3 times √3/4 plus √3 times 4/4. So then this will be 3√3/4 plus √3, which is 7 √3/4. Okay, and we want the ratio of the area of the triangle to the pentagon, so we do this over this. So the √3's will cancel, and then we just have 3/4 over 7/4. So the over 4's will cancel, and then we just have 3/7. So yeah, that's your answer, 3/7. Okay, number 5, a sphere is pressed. Oh, anything you want to say there, Bo?
Um, um, let's see. I got like, I have a, what is it? Actually, no, I think I'm good. I'm good. Yeah, the equilateral triangle formula, it does come in very useful. Uh, yeah, there's nothing really much to say. It ends up just being you find the equilateral triangles and then you solve for the area. So yeah.
Yeah, okay. Number 5, a sphere is pressed part way into a soft plaster mold, leaving a shallow crater that is 18 inches wide and 2.5 inches deep. What is the radius of the sphere? Express your answer as a decimal to the nearest hundredth. Okay. So, um, so it's like we press a sphere into into a mold, I guess, and it deforms the mold into the shape of the sphere, right? So then like the mold is like surrounding the sphere, maybe like this. And and then it leaves that crater right there, right? And that crater is, if you look at it, if you look at it directly, like right here, it's going to be 18 inches wide. And then if you look at it on the side view, it'll be 2.5 inches deep, right? So we can also put this 18 inches like right here, right? Okay. So it's basically like we're taking like a cross-sectional area of the sphere, and we see that that circle that we see right there is 18 inches in diameter, and it's 2.5 inches from the outside of the sphere, I guess. Okay, and then we want to find what the radius of the sphere is. So we probably want to try drawing some things to see if we can get anything here, right? So maybe draw the center of the sphere and then connect these lines. Okay, so we know that this is 9 inches, right? Okay, so we know that this is the radius, and because this is the entire radius, then this length right there will be r minus 2.5, right? So then we can set up a Pythagorean theorem equation right there with that right triangle, right? So we can have r minus 2.5 squared plus 81 squared equals r squared. And then we will have r squared minus 5r plus 6.25 plus 81 equals r squared. So the 2.5 squared, I just did like 25 squared divided by 100. But you also have a calculator, so you can just do it like that. Yeah. Okay. And then the r squared is canceled, so that's really good. Then we just have an r, so we should be able to find an answer here. So we'll have negative 5r equals what? 87, negative 87.25. And then just use your calculator. R will equal what? R will equal 17.45, and it wants us to express our answer as a decimal to the nearest hundred. So this should be your answer. Yeah, that's your answer. 17.45. Um, so not that bad really. So whoops. So I would just say try to get all your information into like this one diagram that I drew, and then just try some stuff. I just connected a few points to get some r's in there, and then I set up an equation with a right triangle. And there are probably a lot of other ways to do this as well. So yeah. Anything you want to say there, Bo?
In response to 1001, who said, "This shows how bad I am at, reminds me of how bad I am at 3D geometry." This problem, like the whole thing about this problem is that you're moving, yeah, like Lishan said, you're turning the 3D diagram into a 2D diagram. This is essentially a 2D problem. So, yeah.
Uh,
Yeah.
yeah, you want to turn the 3D diagram into a 2D diagram. Yeah.
Yes. 3D is very hard to work with. In most circumstances, you will be turning that 3D diagram into a 2D diagram to work with.
Yeah, like all of our equations are like in 2D, I guess, right? So yeah. Um, okay. Let's move on. Number 6, when adding using the standard method, it is sometimes necessary to compose or carry a 10, 100, or 1,000. For example, when we add 15 to 16, we get 11 ones and we compose a 10. For how many ordered pairs AB of 3-digit numbers, A and B, does the addition A plus B require at least one digit to be carried? Okay, interesting. So, um, okay, so we have an ordered pair of 3-digit numbers, and we want it so that when you add those two 3-digit numbers, at least one digit will be carried. So, a better way to do this rather than counting the at least one digit to be carried is counting the no digits to be carried, right? And then subtracting that from the total 3-digit numbers. So because like counting if you have no carries is probably easier, and yeah, you can just subtract that from the total number of cases. So let's do that, right? So we're counting if you add two three-digit numbers and they have no carries, right? So we should first look at the sum of the first digit numbers, right? Um, yeah. So we should look at the sum of the first digit numbers, and we don't want any carries, right? Which means what? The sum has to be less than or equal to 9. So then, what kind of pairs do we get? If this digit is 0, then the next digit can be in the set 0 through 9, right? So this is 10 numbers. And if this is 1, then this digit can be in the set 0 to 8, right? So this is 9 numbers. So this is going to continue with all the numbers until you get to what? Until you get to 9, and 9 just has 0, right? So then our total number of cases for this is just the integers of 1 through 10 added together, right? Which is just going to be 11 times 10 over 2. So this is the sum of the first and last two numbers, and this is the number of numbers we have, and we divide it by 2. So then this is 55. So we have 55 cases for this, right? And this is like totally what? This is totally separate to our other digits, right? So basically, we can count up the cases we have for our other digits too, and we just multiply all three numbers together, right? So we have 55 cases for this one, and the second digits have like is the totally same case as the first digits, right? Because you can still have 0 and like it's not affected at all, right? We have no carries, so it's not going to affect them at all. So it's still going to be 55 cases. But the last digit is or the first digit, I guess. Yeah. The first digit is a little bit different in that you can't have zeros in any of them, right? Because they have to be three-digit numbers. So then what? Then this case goes away, and all of these zeros go away, right? Which means what? Which means we have to subtract 10, and we have to subtract 1 from all of these. And there are 9 of these, so we have to subtract 9. So we have to subtract 19 from 55, which is just what? 36. So then there are just 36 cases for this one. And then if we multiply that together, we get 1,089,00 cases. And then we need to subtract this from the total number of cases, right? So we have an ordered pair of three-digit numbers. So we have 900 possible three-digit numbers, right? So the possible number of ordered paired three-digit numbers is just going to be 900 squared, right? Which is it's just 81,000,000, right? And then we subtract that. So there we go. And then we get 701100. Let's see if this is correct. Yeah, that's correct. So yeah, that was kind of surprisingly easy. I don't know. It seems a little bit easier than the last problem. But yeah. Anything you want to say there, Bo?
Right. Yeah, like 1001 said. When you see when the question is asking for at least one, like at least something, and it's like either probability or just like how many of them are at least, that's you should instantly just think of total minus the stuff that's not. That's like a dead giveaway. That's what you should use. In
Yeah,
terms of the question itself, I mean that's not really that bad. There's nothing really that bad to the question itself, so there's nothing really to say there. Yeah.
yeah. All right, let's move on. Number 7. This array is composed of, oh, this one? Oh, yeah, that's that one. Okay. This one is spicy. Woohoo. Okay. This array is composed of congruent equilateral triangles. 3 vertices within the array are joined to form a shaded non-equilateral triangle as shown. what fraction of the triangle with the dotted line with the dotted outline is shaded? Express your answer as a common fraction. Okay, what is this? So we have an array of equilateral triangles. We have 3 points and they form a shaded triangle, right? And then there's an equilateral triangle right here. So it cuts off like that little part, right? We want to find the ratio of the area of the shaded part of the equilateral triangle to just the whole area of the equilateral triangle. Um, so so first looking at this, um, yeah, you can find the base and height of the shaded, but that doesn't really help that much, right? You want to find how the shaded triangle relates, like how it cuts off this triangle, right? Which is kind of weird. Like just doing it into like I don't know. I think just doing it like with regular geometry, it's kind of hard to do stuff to try to find what the area of this shaded part is going to be. I think a lot easier way would just to be just to do chord bash here. Um, because essentially you know where these 3 points are, and you know where this is as well. Um, yeah. Do you have anything to say to that, Bill?
Well, the people in chat are they do not like it, I think. Um, yeah, coordinate bash was like the solution we thought. Can we put the pieces of the shader region together to make an equilateral triangle? Um, well, the
Wait,
thing
what
is,
do you mean with
the
that?
thing. Okay, I was just reading chat. The thing is about putting the pieces together to make equilateral triangle. That is that yeah, that doesn't really do anything. It doesn't get you anywhere closer to You probably can, like looking at it, you probably can, but it doesn't get you anywhere closer to the answer because you're looking for the only in the smaller triangle. So honestly, yeah, I'll just corner bash this. Yeah, shoot. Basically, what we were thinking of is to just coordinate bash the coordinates of the coordinates of the three vertices of the triangle, and then use Shoelace theorem to get the area of it.
Yeah, yeah. Okay, let's do that. So, how we can find the coordinates of these vertices, these intersecting vertices, is by having like the equation of this line, having the equation of this line, and having the equation of this line, right? And we just find the intersecting points. So so we can put our coordinate plane with origin at this point. So then what? Then if we just look at the points of the shaded triangle, they're going to be 0, 0. And let's say the lengths of the equilateral triangles are 1, right? Um, we can have the lengths to be anything. So yeah. So then this point would be at 4, 0, and then this point would be at what? It'd be at 3.5, so 7/2. And then what? So all these are √3/2. So then it would be up. Whoops, sorry, I'm bad. It would be up 3√3/2. Okay, and then so the equation of this line would just be the line with a slope of 3√3/2 over 7/2. And it crosses through the origin, right? So it's not going to have any y-intercept, so it's just going to be like this, right? Um, so this is just what the over 2's cancel. So then we have 3 times root 3 over 7 x. So that's the equation of that line. And then what are the equations of these lines, right? So this horizontal line is just y equals root 3, right? Because it's it's at the y equals root 3 horizontal line. So yeah. Okay. And what's the equation of this line? So uh well, we can just find the coordinates of like 2 points there, and we can just do it from that. So that point right there is at 2 root 3, and that point right there is at 5 halves root 3 over 2. And you should probably like if you're working this out, you should probably like double check it so that it is true, because you can make silly mistakes on this, and then your answer will be wrong. Okay, and then what? Then the slope will be root 3 over 2 minus root 3 over 5 halves minus root 2, which is negative root 3 over 2 over 1 half, which is just negative root 3. Um, and um, and then we use point slope formula to find the rest of the equation. So we're gonna have negative root 3 times x minus x minus 2 plus root 3. So this is our equation, and this is what? Negative root 3x, and then we have plus 2 root 3 plus root 3, so it's plus 3 root 3. Okay. And then what are our equations? We have this right here, and this right here. So what we can just do is we can put this one with like this one in our calculator and find the point of intersection, and then put this one with this one to find that point of intersection as well. So let me just do that real quick. Um, all right. If you put this one with this one, then you get x equals 7/3 and y equals root 3. So basically that point right there is going to be 7/3 root 3. And let's do the same thing but with the other equation. Okay, then we get x equals 21/10 and y equals negative root 3 over 10. So that point right there is going to be 21/10, comma, negative root 3 over 10, right? And then that point right there is just what? Is 2 root 3, right? So then we have the 3 points of this tiny triangle right there. So we can use the shoelace theorem to find the area of that small triangle. And then we can put the area of that small triangle to the big triangle and then subtract that from 1, right? To find the ratio of the shaded region to the big triangle. Yeah. So yeah, then just apply the shoelace theorem, right? Does everyone know what the shoelace theorem is? Here, I'll just say it anyway in case people watching don't know. So it's like you have any polygon, okay? So any polygon in the coordinate plane. So maybe it looks like this. and it can have any number of vertices, right? And it could be whatever. It could be anything. Okay, and let's say you have the coordinates of all the points, right? So I can just have this as x1, y1, x2, y2, and then just have that for all the points. So how many points do you have here? 6, right? So this will be x6, y6. Okay, and then it is the most chord-bashy formula in geometry. Yeah. Okay. So then what you do, the theorem lets you find the area of this polygon. So what you do is you put all of the coordinates in a column. Okay, and you line up the x values and the y values like this, and then just do this all the way. Okay. And then this is where the shoelace part comes in. So what you're gonna do is you're gonna multiply xy or x1 times y2. Okay, and we can put it here. x1 times y2. And then we're gonna multiply these two together. Oh, why is this 2? This should be 1. We're gonna multiply these two together and we're gonna subtract that. So we're gonna minus x2 times y1. And then we're gonna move our weight down. So we're gonna do this to here now. So we'll have x2 times y3. And then we're going to subtract this part. So we're going to subtract x3 times y2. And we're going to do this for all of them, right? So we're going to have a bunch of stuff. And we also want to do this to the last one as well. So it's like we have the x1, y1 right here. And we just do this one last time with this. So then we have x6, y1 minus y6, x1. And then we add up all of this stuff together. And then we divide it by 2. And the answer could be negative. If it is negative, then the answer will just be the positive version of that. Yeah. So you have to absolute value what it is, and you have to remember to divide it by 2. That's crucial. Yeah. All right. So let's apply that to our thing here. So this is very good on our thing, right? Because we have the coordinates of the vertices of the triangle, and we want to find the area of the triangle, right? So that's perfect. So, oh, by the way, when you're listing out the coordinates like this, you have to put it like you can start at any point and then you can go to some other point, but then you have to like follow the lines of the polygon. But we have a triangle here, so really any order works, so it doesn't really matter. So I can literally put it in any way I want to. So yeah. So then we just do it like this. All right. So then we're going to have 2 root 3 minus 7/3 root 3. And then this is kind of not very nice numbers, but yeah. We're going to have 63 times root 3 over 30 minus 21 root 3 over 10. And then here we're going to have 21 over 10 times root 3 minus 18 root 3 over 10. Okay, so all of these have root 3, right? So we can just add up the coefficients of the root 3. So let me do that. And if you put it on the TI, it just gives you a fraction, not a decimal. So that's pretty good. Then you just have the fraction version of it. So yeah. Okay. So if I put the coefficients all into the TI, I get negative 110. So and they all have root 3, right? So I have to have root 3 here. Okay. Oh, not 110. It should be negative 1/30. Yeah. Okay. So then we take the absolute value of it and we divide it by 2, right? So then the area of our small triangle should be root 3 over 60. Okay. And then we want to put this into a ratio of the area of our whole triangle, right? We set the side lengths equal to 1, which means that the area of the whole triangle will be root 3 over 4, right? So then the ratio of the area of the small triangle to the whole triangle will be this, right? So the root 3's cancel, and then we just have 4/60ths or 1/15. But this is not our answer, right? we wanted to find the ratio of the shaded area to the whole triangle area, right? And this is the ratio of the non-shaded area part. So then the ratio that we want to find is just 1 minus this, right? Which is 14/15. Okay, and then oops. And then yeah, that's our answer, 14/15. Yeah, again, I think geometry would be way too bad here. I don't even know where to start with it. This seems, I don't know, this seems like a pretty obvious chord bash problem to me because like you have like weird segments and stuff, right? But you have like you can set up a thing where you know the like coordinates of everything, right? So yeah. Anything you want to say, Bill?
Right, so I just want to talk about 1001. He says, "Oh, geometry is so bashy and stuff." I mean, geometry is not always like that. Coordinate bash is just like something you can always fall back on. It's just like if you can't find anything, coordinate bash is something that most of the time will completely work. Yeah. Um, but you will come across geometry problems that are like you can do them. They're nice to do. They're fun to do. Like they exist. But for this problem, the nice thing and the only reason we could do coordinate bash on this was because you do have calculators on this question. So that's the whole reason why we could do because without calculators this will be way
Well,
too hard.
no, I think you can also do it without
Well,
calculators.
yeah,
I
but
I
the calculation
like
it wouldn't be as nice. Like it'll take longer to do.
like it can also it can also work without calculators. It's just a little bit slower. Um, but yeah, but it makes sense that they give us core bash problem on when we have calculators.
Yeah. Um. Right. And also for just for the shoelace theorem it might seem bashy, but like once you do it a lot, it honestly stops feeling bashy. At least to me. Like it's just another tool. It's not really that bashy once you get used to it.
All right, all right. Sure. Let's move on to our next question. When an unfair coin is flipped 5 times, the probability that it lands heads up more times than tails up is 31 times probability that it lands heads up 5 times. What is the probability of the coin landing heads up on one flip? Express your answer as a common fraction. All right, we have a probability problem. It's it's not counting. Or I mean, maybe you could do this with counting. I don't know. No, it's probability. Okay. Okay, so okay, so we have an unfair coin. Let's just say the probability of it landing on heads is X, right? Okay, so then what? We flip it 5 times, and it says the probability that it lands heads up more times than tails up is 31 times probability that it lands heads up 5 times. Okay, so the probability that it lands heads up 5 times will be X to the fifth, right? And 31 times this probability is the probability that it lands heads up more times than tails up. Okay, so we should look at the probability that it lands heads up more times than tails up in terms of x, right? Okay, so well, we can just separate it into cases. So there's the 5 heads case, 4 heads case, and 3 heads case, right? So these are the cases where we have more heads than tails, right? Okay, so 5 heads case, this is just x to the fifth, right? Pretty obvious. 4 heads, um, you're gonna have x to the fourth times 1 minus x, right? but you're also going to have to think of the arrangements. So how many arrangements can you have with four heads and one tail? It's just going to be five, right? So we're just multiplying this by five. And you can also think of it as just five choose one or five choose four. Yeah. And then three heads will be x cubed times 1 minus x squared. And then times five choose three or five choose two. And that is just what? Uh, that is just 10, I believe. Yeah, that is just 10. Okay. And then so then we just have this equaling x to the fifth plus 5x to the fourth times 1 minus x plus 10x cubed times 1x squared, or 1 minus x squared. And then we just have what? 30x to the fifth minus 5x to the fourth times 1 minus x minus 10x cubed times 1 minus x squared. Now, yeah, this is a quintic function, right? But there's nothing the TI can't handle, right? So yeah, so we should just put this equation into our TI and see what it gives us. Um,
Is what allowed?
it, yes, what?
Just putting the equation. It's the calculator is legal, so and it's a
Yeah,
function and yeah, the calculator is legal and yeah, it's a function in the calculator, so it is allowed.
yeah,
So yeah, things like
um,
these simplify it way down.
yeah. I mean, I'm not sure. Like, I actually don't like calculators much. I don't know
Yeah,
because
Austin
like,
doesn't
or
really
like
like them.
not
Austin,
when you like not when you let like really good calculators like TI being used
yes.
because 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 like I debated on this a lot. Like you can program functions into your TI and it's really powerful. So then you can just have functions for like everything into your TI and then you don't have to do anything. So I don't really like that. But like it's a little bit better in Mathcounts because like the Mathcounts problems are pretty unique. So you can't really like you know have functions for all the possible math counts problems that there are. But like it's really bad in high school UIL math, in my opinion, because the high school UIL math problems, like they are so like I don't know, like generic, like they have tons of repeating problems, and yeah, they're like totally programmable. So like I would say like you can have like probably like 70% of the high school UIL math problems just like programmed into your TI, and then you just plug in like numbers, and then the rest you just do a little bit of math. And like the best way to to compete in high school UIL math is actually to have the functions on your calculator because it saves you a lot of time, right? So then the competition just becomes like who can program like functions the best on their calculator. So that's why I really don't like it. But yeah, it is better on math counts because math counts problems are more unique. Um
Right, like
yeah, I like AMC better because they just don't have calculators
right.
and I like the problems, yeah.
Yeah, calculators eliminate like a big aspect of just like problem solving because a large aspect is of problem solving is like you're thinking of how to make the problem doable, and then with a calculator you can just straight bash it and like yeah.
Yeah. Why do they have calculators for high school UIL math? Like they even didn't have calculators in middle school, but then they had it in high school, and I just think that made it totally bad. I don't know. And they even have a calculator test, but they still have a calculator on the math test. So I don't know.
Yeah,
I don't
like
know, man.
no, okay, yeah, like Like for high school calculator, no, for high school UIL math, like it's basically just who has better functions on who has better programs on their calculators, and that's basically
Yeah.
it.
And then you just need to know like a little bit of math for the problems that you have in program. And and guys, do you know they also have questions on what? On math, like history, like on every test they have one question on it. It's like it's like I don't know who is the father who's often called the father of geometry. And then they have like Euclid and I don't know, just a bunch of people. And then yeah. So
They also make you memorize the all the
oh,
different
and they
types of
also
numbers.
yeah, they always have a few questions on like just wacky stuff.
Yeah, like
Like
evil
what is the
numbers.
sum? Yeah, what is the sum of the first three evil numbers? Or something wacky like that. So you also have to have like yeah, so you also have like lists of those weird numbers in your TI and you just look it up. Um, yeah, I don't like it having yeah, like you shouldn't try to know all the weird types of numbers. Like they really like don't matter most of them. Um, I don't know why they asked them, but they just have it. Like
Yeah,
yeah, I definitely don't know what all the weird types of numbers are. I just have it in a thing on my TI.
right. Like for most of those numbers, I've never seen them used outside of UIL. UIL is the only place where I have seen most of those numbers.
Yeah. All right. So so yeah, back to our thing. If you put in the function into your TI, oh, what is the evil number?
I,
You can
I'm
just search it up.
I'm not good at UIL, Austin. You can do this. You can tell
Evil number. In number theory, a evil number is a non-negative integer that has an even number of ones in its binary expansion. These numbers give the position. Oh, okay. So it's like I think it's like let's say you have five, right? And you binary expand it. So you put it like so five in binary is what is 1 0 1. So five is the evil number, right? Because it has an even number of ones. Yeah, so that's like totally arbitrary, right? Like, when are you ever going to use that? It's just totally random. So yeah, all right, rant over. So if you put this function into your TI, you'll get x equals -1, 0, or 2/5, right? And it can't be -1 or 0. Well, it could be 0 actually, right? It never specifies like it can't be 0. Common fraction? Okay, sure. Well, the answer is obviously going to have 2/5, right? Okay. So yeah, um, yeah. We set x as that, so yeah, the answer is 2/5. So yeah, this problem was not that bad. Yeah. All right, let's move on to team. Team is really spicy. Yeah, A was
Oh,
really easy.
team was really interesting. Let me
Uh,
say that.
yeah, team is really spicy. Yeah. All right.
Please let
Okay.
there there is there's always geometry. Geometry is a certainty in life, okay? You
Yeah.
just have to
Yes.
you just have to learn to be able to deal with geometry problems if you don't like them. Because they'll always be there.
All right. Um, Mrs. McWitt has 35 desks numbered 1 through 35 in her classroom. If three students randomly sit at three different desks, what is the probability that each sits at a prime numbered desk? Express your answer as a common fraction. All right, we should try to find the prime numbers from 1 through 35. So, yeah. So just so yeah, we need to find the prime numbers from 1 through 35. Okay, yeah. So let's list the primes, right? So we're gonna have 3, 5, 7, 11, 13, 17, 23, or 19. I missed 19. 29, 31, and that's it. All right. And we just need to count how many primes there are. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 primes. Right. Did I miss any? Oh, I missed 2. Nice. I'm really good. All right. And I also have a function on my TI. If you give it a range of numbers, like two numbers, it will find all of the prime numbers in that interval. So that's pretty cool. So like for this problem, I could have just put that function with a 1 and 35 and it would list all the numbers. So I programmed that function into my calculator. I actually did it for UIL because yeah, like I just talked about it, like to do well at UIL you need a lot of like functions. So yeah. Um okay, so we have 11 primes, right? So we have 11 primes and 35 desks. So what does this mean? The first person probability they sit at a prime number desk will be 11/35ths, and then the second person will be a 10/34ths, and then the third person will be 9/33ths. So then we just multiply all this together. Yeah, you also have a calculator on Team. Oh, then you get 3/119. And then yeah, that's your answer. So not that bad. Marcella builds a model pyramid out of cubes, each of length 1 inch. She starts by making a 10 by 10 square base out of the cubes. Each additional layer of the pyramid is a square array of cubes with one fewer cube per side than the layer below it. So like the second layer will have a 9 by 9 square and then it'll go all the way up, right? The top layer consists of one single cube. If the pyramid is on the ground so that the bottom is not exposed, how many square inches of surface area are exposed? Okay, so yeah, we have like a if we're looking at it by side view, it's like we have a 10 by 10 square here, right? And then we have a 9 by 9 square thing here, and yeah, we want to find the surface area that is exposed. Okay. Oh no, it's not. That's for the next problem.
There is no diagram.
Yeah. Okay. So how we can do this is is it's like I don't even know. It's just like being clever with it. So like if you look at the pyramid from a bird's eye view, what is it gonna look like? We're gonna have a single cube here. We're gonna have a 2 by 2 square here. Um yeah, and then we're gonna have 3 by 3 here. And then we're just gonna go all the way, right?
This is the copy
So
of the
dot dot dot.
2020 10B problem. Yes, this is very similar to that problem. Austin, do you remember that problem? In 2020
10B?
AMC. It was on 12 too. It was on 12 too.
Oh, what's on 12?
Yes, it was the one where they stacked
Oh
the cubes.
crap.
Do you remember?
Yeah.
Yeah, it was A.
Oh
It was
crap.
A. Yeah, it was the one where
Wait,
they
what?
stacked the cubes. Do you remember?
Yeah. Wait,
Okay,
what
yeah.
was it asking?
It was also asking for surface area of the stacked cubes.
Oh, really?
Yep.
Oh, surface area. Yeah, I remember. Okay. Okay, yeah. So if you look at it on a bird's eye view, the total surface area is just gonna be like the surface area of the like the area of the 10 by 10 square, right? Because like it totally encompasses like all of the stuff, right? So basically the top surface area of all the cubes will just be the area of the 10 by 10 square, right? Which is just 100. And then we just need to find like the side exposed area, which should not be that bad. So like the exposed side area of this 10 side will be 10, right? And then this will be 9, this will be 8, and so on to 1. And then we need to multiply this by 4, right? Because we have 4 sides. So then we just have 1 plus 2 plus all the way to 10 times 4. So you use the sum formula, it's just going to be 10 times 11 over 2 times 4, which is 220. Yeah. Okay, and that should be all of our surface area, so then it would just be 320. Yeah, that's our answer. When the array shown here is completely filled in, each circle contains a number. If the number in each circle below is the top, if the number in each circle below the top row is the sum of the two numbers closest to it on the row above, what is the value of x? Okay, so what this is saying is like this circle right here, this is going to be the sum of the two circles above it, so 6 and x. So this circle will be like 6 plus x. And like this circle will be just 6 plus 3 or 9. And then we want to find what the value of x is, and we have 1 down here. Honestly, the only way I see to do this problem is just to like fill everything in. Um, I'm not sure. I'm not sure if there's I don't think there's any other good way to do it. Maybe there is, but I don't know. I think you just sum all the numbers. What do you think, Bill?
Um, right.
I mean, on the test, I would definitely just fill it in, right?
Yeah, like
Because
you
I
would just
see,
definitely fill it because also this is team. You can have multiple people fill it in. I don't know, but yeah, you would have. Yeah, I think you would just fill it in. There's actually not
yeah,
that
filling it in
many.
won't be that hard.
There's not that many, so I
Yeah,
think plugging it in wouldn't be that bad.
yeah. But I don't know. I guess I don't really like this problem because it's like
Really
it's so
bashy.
easy. Like you don't think about it at all, and you
Yeah,
just bash.
yeah, it's really
Like,
bashy.
oh oh yeah, I can do that. Hold on, let me get it real fast. Uh, I can give you the link where we get all of our problems from, so you can just get it from that all the time. So that link, it has like all the Mathcounts problem of school to national from 2017 to 2000, and um some of them have solutions as well, and some of them have countdown rounds. Yeah, no problem. Wait, do you guys think we should do countdown? Or I don't know. Yeah, okay. All right. So yeah, you just bash this out, right?
Right, if
So
we do countdown, it will be more like just speed focus, like just like I don't know, showing like, because countdown like in the end, countdown will be just like knowing all the problem types, memorizing all the problem types, and then so you can get them, like you see the problem, you know what it is. That'll basically be countdown.
um, yeah, we, I don't know. Maybe we can sometime like maybe maybe Christmas break or sometime just like do one countdown thing for fun. But we probably shouldn't focus on it too much. Like it's not really like I don't know. It's not a big deal until nationals, and and it's really speed focused, right? So so not really like
It's focused on like just memorizing the problem types and stuff like that.
yeah.
Like memorizing the problem types. So like the moment you see the question, all you have to do is just like know which one it is, and yeah, Luke would kill us. Yeah, those kids are insane.
Wait, what grade is Luke in?
Oh, isn't he like a ninth? Oh man,
Ninth right
we're
now?
older than him. All right.
Oh, damn. Okay. Oh wait, he's in 10?
Oh shoot, 1v1. Let's do it.
Oh dang.
Hit.
Wait, that's cool if he's in our grade.
Oh yes, hit me up, Luke. I wanna see who's better at math, you or me.
Yes. And what if Luke watches this video?
You better accept my challenge then. Better leave a comment. Luke, if you see this video, leave a comment, and I'll email you. We can set up something.
All right. Um, okay. So I got at the very end 28x plus 225, and we're gonna set this equal to 1. So let's see if we see what we get. Okay, I got x equals -8. And yeah, that's the answer. Yeah, this is just so bashy. I don't get the purpose of this problem. Like, literally anyone can understand it, and you just bash. Um, it's whatever, I guess. Let's move on. A piece of fencing is made using a rectangular iron frame and several lengths of metal wire that span the interior of the frame. The wires form 45-degree angles and are attached to the back of the frame. In the interior of the frame, the wires intersect each other to form squares with 3-inch diagonals, as shown. How many feet of metal wire are visible within the frame with inner dimensions of 6 feet by 8 feet? Express your answer in simplest radical form. All right, what is this? We have a box, and it's 6 feet by 8 feet. And we have a bunch of diagonal lines. And maybe I should just copy the figure.
Maybe you should.
Yeah, I'll do that actually. Maybe I should. I just put this in. Oh, does it work? Maybe not.
It could be
It's
further.
nothing.
It could be somewhere else in the thing. It could be like somewhere else in the document.
Oh, yo,
You got it. Nice.
how do you scale this up?
I don't. I don't know. I've never used Adobe.
Oh,
Whatever your Adobe Illustrator.
all right, yeah. Okay, it looks like this, right? And it's, oh, what the heck? I can't draw on it? Wait, what? My pen doesn't work. Is it on a white or something?
Layers. It's check if you're on the right layer or not.
Wait,
Hang on. It could be a. The picture could be on a layer that's higher than the
no, it was on white. It was on white for some reason.
Oh, it was on white? Okay, I guess.
Okay, so yeah, this side is 6 feet, this side is 8 feet. So first note, we have different units, which is kind of bad or trash, I don't know. So be careful of that. Also, this is not like to scale, right?
Yeah, this
Um,
is not to scale at all.
because if we had these are all 3 inches, right? And that would be 1 foot, but this is 6 foot, right? So yeah. Oh, okay, yeah. So so we can do this in multiple ways. One way we can think about it is think about how many of these triangles are we going to have on each of these sides? So 4 triangles is 1 foot, right? So we're going to have 24 triangles on this side, and we're going to have 32 triangles on this side. Um, so so yeah. So basically so okay, so 32 triangles here and 24 triangles here. And these 24 triangles are going to connect with 24 of these triangles, right? And we will have 8 non-paired triangles right here, right? And these will just go like that. And then this, wait, what? Yeah, okay. And then we're gonna have another of these 24 by 24 triangle things here, right? 24 by 24. So that, because this only goes 8 here, right? So then this 24 will make it 32 here. And then this 24 matches up with a 24 here. That's a really weird drawing, but yeah. Okay, and then we should think about the lengths. So what we can do is just find the like one-way lengths and then double it to find the other other like direction diagonal lengths, right? All right. So what we can do is find the lengths of these 8 diagonals that we had. Um, and then find one of these the lengths of like these one of these triangles and then double it to for the other triangle, right? Um, yeah, yeah, that should work. All right. So how long will these long diagonals be? Um, well, they are if we look at them, they are 24 long this way but also 24 long this way, right? Um, because it goes like all the way from here, so it has to be 24 in this way, and it's like 45 degrees, right? So it also has to be 24 this way. So that means the length of it has to be 24 times root 2. So then for the 8 of those, it's going to be 8 times 24 times root 2. And then what are these going to be? Well, the first diagonal of this triangle will still be 24 root 2, right? Because it connects, wait, will it actually? Uh, no, I don't think so. Because, it's like the 24 triangles, wait, uh, no, it would. Yeah, it would. It's like, it's like we're making the triangle here, right? And this triangle is of full length. So the first diagonal is going to be full length. So the first diagonal is going to be 24 times root 2. And then the next diagonal is going to be, like we can look at it here, like pretend this was the next diagonal. It's going to be 3 inches shorter here. And so 3 inches shorter here as well, right? So we're working in inches, right? So the next diagonal will be of 21 and 21, right? So then it'll be 21 times root 2. So the next one will be 21 times root 2. And then we're going to do this all the way to just the smallest length, which will just be three inches on both sides, which will just be 3 times root 2. And then we just add all of this together. So so this will just be 8 times 27 over 2 times root 2. And we need to double this, right? Because we have another triangle there. And then we need to add this to our 8 diagonal things. And then we need to multiply this by 2, right? Because we counted all the diagonals in one direction. So we need to have the diagonals in the other direction as well. All right, so what is this going to be? This is going to be these two cancels out, right? So then we can just look at the coefficients of the root twos, and then we get 816 times root 2. All right. Oh, there's 1 in feet. Yeah, 1 in feet. Okay. So we divide by 12. So then we get 68 times root 2 feet. Uh-oh. I did something wrong. My answer was really off. Uh, do you know where I went wrong, Bill?
I'm thinking about it. Um, well, everyone's getting different answers.
My answer was really off, though.
It's really off,
Like,
and
not like a small mistake.
it's not even, it's like you can't multiply by something to get the final answer. So
Hmm. Oh, okay. I see. I see where I went wrong. So, I said these were 24 triangles and 32 triangles, right? But I used that as inches, but that's wrong, right? Because the actual length will be like three times the number of triangles, right? Because the triangles are like 3 inches long there. So like all of these lengths should be tripled, right? I think. Yeah. So then my final answer should be triple, but that's not right either. Then I get 204 times root 2. Wait, actually, I don't think it would just be triple because then the sum would
It
be
wouldn't
like
be
different.
triple because
Yeah, let me just do it again.
there's the other lines to consider.
So these are 72 inches actually. So the diagonals are going to be 72 times root 2. We're going to multiply that by 8. And then we're going to have the sum is going to be 72 times root 2, and it's still going to go down by 3 every time. So now 69 root 2, and then we're going to go so on, the way to 3 root 2, right? So this is going to be 75 times what, 24 over 2 times root 2, and we're going to double this. So this is going to be 75 times 24 times root 2, and then we're going to double all of this, right? So let's see. Let's see what that coefficient is. Oh, whoops. It should be like this, and then that times 2. Okay, and then you get 4752 root 2, then you divide it by 12. Oh, and then you get 396 root 2. That's that's pretty close.
That is 12 off. So if you look back, what could you have overcounted that would make 12? Um,
We could have overcounted the diagonals somehow. Um, so we can look here, right? So in this depiction, we have 4 triangles by 6 triangles, right? So we have this is like the triangle that we made, right? So this is 4 triangles by 4 triangles, and so is this triangle, right? 4 triangles by 4 triangles. But we actually only have one diagonal. So the diagonals should not be 6 minus 4, but they should be 6 minus 4 minus 1, right? So like if we added 1 to here, it would add 1 diagonal, right? And if we added 1 to here, it would subtract 1 diagonal. So instead of it being 8, it should be 32 minus 24 minus 1, right? Which is 7. So then we need to subtract 2 diagonals, right? So subtract 2 diagonals, we're gonna subtract 2 times 72 root 2 over 12. Or over 12. Um oh, and then it's minus 12 root 2. And then yeah, you get 384 root 2. So yeah, you need to be careful with those diagonals right there. I probably should have thought about it a little bit more. So, but yeah, a good thing to do actually is to like kind of use the smaller diagram and just see how it apply to the bigger diagram. And yeah, so that was also what I was gonna say. Another way you can do it is like by like separating this essentially. Like separate it into smaller rectangles and then find the lengths of those rectangles. Yeah. Anything you want to say there, Bill? So I don't think this question is very hard, but there's just a lot of mistakes you could do.
Yeah, it's not a very hard essentially it's not a very hard problem in essence. Like you're just finding the length of the lines. It's just like, you're converting so much stuff, like it's easy to make mistakes.
Yeah. Do you guys want me to like do it another way, like the four quadrants way, or just move on? Sean, what do you think? Let's just move on. Um, it's really not too hard. Just a lot of mistakes you can make. All right. Oh wait, what? Why did we start there? Okay. Um, when each circle in the given diagram is filled with one of the numbers 0, 1, 2, 10, 11, 12, 20, 21, or 22, a number may be used more than once. We call it a happy assignment if, for every arrow, the values at the two endpoints have positive difference 1 or 10. How many happy assignments are there? Okay, so so every one of these pairs they had to differ by 1 or 10, and we can only use a specific set of integers to put in the circles. We want to find the number of happy assignments. So one happy assignment could be like what? 0, 1, 11, 12, 22, 21, and it goes back to 11. All right.
Wait, Austin, you're gonna do this problem?
No, but um so okay, so when me and Bill were working this out beforehand, um we were thinking of like let's the so okay, so we thought about putting the numbers in like having the numbers in three sets. So the three sets of numbers are 0, 1, 2, 10, 11, 12, and 20, 21, 22. And you can see in these three sets, they're like aligned, right? they're aligned in like you can go from like 0 to 10 to 20, 111 to 21, and 212 to 22, like that. And you can also move around in the sets. So essentially you can have it like A1, A2, A3, B1, B2, B3, and C1, C2, C3. And it's like you can go to another nearby um letter, or you could hop to a different letter, but it has to have the um same subscript number. Um okay, so me and Bill thought about this um for a while. We were just thinking of like um all the cases. Okay. So like maybe let's start with A1, all right? A1 in this very tail right here. Or actually, we probably shouldn't do that. We should think about the square because the square like limits it the most. So we should think about the square first. So let's think about if we had just A1 in that square corner. Let's just think about the square. We're not even gonna think about the tail yet. Um, okay, if we have A1, where can we go? Well, we can go to B1, we can go to C1, come back to B1, and then we're at A1, right? Okay. What are some other things we could do? Well, we could go to A2, A3, A2, and back to A1. All right, and what are some other things we can do? Well, we can go to A2, B2, and then back to A2 and back to A1. Well, what are some other things we could do? Go to A2, B2, but instead go to B1 and then go to A1. Okay? Is there anything else we could do? Um, A1. Oh yeah, we could go like A1, B1, B2, A2, A1. Um, yeah. So like all of these you can have like reflections of them, right? So in this way or in this way. So like so this one could have been like C1, B1, A1, B1, right? Then you can also have rotations of them, right? Or this one is actually just these are just rotations of that, right? Um, but yeah, you can have rotations of them as well. Um, so all of these are going to have rotations. Um, and I don't know. This is just for A1. If we look at the other ones, it's also going to be weird. And I don't know. Um, basically, like there are a lot of cases for this, right? Maybe this is doable, but it's kind of hard in the time that we're given with, right? Because like there are tons of cases. Like all these cases that I listed for A1, you could rotate all of them, right? Um, and that was just for A1. Um, we would also have to do it for like all the other ones, but then the other ones they could have repeating ones, right? Like A2. When we use A2, we would have to make sure not to use the combinations with A1 that that like the combinations that we used from A1 that had A2 in them, right? Because then we would be like overcounting. And that's pretty hard, right? And then the tail comes in, right? We have to think of all the rotation stuff. We had to think about which part connects to the tail, and then the tail is going to add more stuff. Um, I don't know. This question is pretty hard. Maybe it's doable in casework, but it's pretty hard. Um, if I were doing this problem on the test, I would probably like maybe try it for like 2 minutes and then realize that it is pretty hard. Um, and then I would just skip it. Um, so you're saying there has to be some nice way to do this? Me and Bill did think about this for a while,
We
and
did. We thought about this for a while, and then we
we
also
really couldn't
asked.
come up with anything except for casework.
Yeah, and
Yeah, we also asked this I don't know. He's like a sorry. He's a
calculus.
calculus teacher at Lokai. Um he also does UIL. He's just like a he's just like a math person at Lokai. Um and I don't know. He's pretty experienced, I guess. So we asked him and he said he didn't know how to do it. Um so then we looked at the score reports.
Yeah,
I think we actually like found the score reports
yeah.
by from this problem because we were like,
Oh,
this
he's
is
saying
pretty
not to
hard.
show
Let's
the
see.
answer, not show the answer. He's saying to not show the answer. But
Oh,
anyway,
sorry,
if you
sorry.
look at that problem, a total of 0 teams got that problem.
Yeah. So we searched up the score distributions because we thought this problem was hard. And we found that
Got this problem.
zero teams got this question right. And I mean that's saying something, right? You have you have what? You have how many teams do you have at Mathcounts? It's
Uh,
224 people, right? Yeah, you have 56. You have 56 teams at Mathcounts, and they're like the best teams. They're like the best, I don't know, middle school math people in the U.S., right? And like they're really good, right? They're like people like Luke. Did Luke compete in
Actually,
2016 or
hang on.
not?
No, let's think about it. Did Luke compete? He might have. Yeah, he did.
He competed all 3 years
Yeah,
in middle school, right?
Even Luke didn't
Yeah,
do.
Luke couldn't even do this one. I mean, he only had like 2 minutes on average,
Right.
or his team only had 2 minutes on average to do these, but still, like he couldn't do it, right? Um, so yeah, it's pretty hard. I mean, I think we should I think we should skip this problem for now and just try to get done with the other ones, and then we can come back to this one later if you guys want to solve it or try to solve it, and we can try to spend a good amount of time on it. But if we can't do it after a while, we should probably just skip it. Or yeah, you could also try it like um in your own time and let us know if you like um get anything done with it. And you can tell us like what answer you get for the problem, and then we can tell you if you got it right or not. But yeah, we're just going to skip this problem for now. If we have time at the end of the class, we can come back to it. But yeah, all right. Oh, also only 11 people got number four right. So yeah, number four, you can make a lot of mistakes there. Um, all right. Number six, positive integer n has a units digit of 3 and is divisible by 7 and 11. Positive integer n has a units digit of 8 and is divisible by 7 and 11. What is the least possible absolute difference between m and n? All right. Um, Easy. Are you talking about this problem? Uh, oh, what are you thinking of doing?
There's a saying that if the problem seems too easy, you're not good enough to solve it.
Wait, what?
Mm, Nothing.
Um, okay. So so one thing that I can do, or I can think of doing here is seeing that both numbers are divisible by 7, right? Um, so if both numbers are divisible by 7, we can just try to take that divisible by 7 out, so we can work with smaller numbers. And then the absolute difference, the least absolute difference that we get from our new numbers, we can multiply that by 7 at the end, right? Um, so so yeah. So if you have a units digit of 3, so we're gonna try to take the 7 out of both of these, right? If we have a units digit of 3 and we take out a 7 from it, then we'll have to have a units digit of 9 afterwards, right? Um, the other units digits should not work here. Yeah. And so n will have a unit digit of 9, and n will have a unit digit of what? Of 4 after we divide both by 7. And they will still be divisible by 11 and divisible by 17 respectively. And so now we just find the least possible absolute difference between m and n here, and then we multiply by 7. Um, and then for this, honestly, I would just start by trying to list some stuff out. Um, so the first thing that works here, as n, it has to have units digit of 9, and it has to be divisible by 11, right? So the smallest n that works is 99. And then and then what? And then the next ones are going to be 99 plus 110, and you're just gonna keep adding 110s, right? So you don't change the unit digit of 9. So the next one you get is 209, and then you add another 110, and then it will be 319, and so on. Okay, what about the unit digit of 4 and 17? Well, if we try to find the first multiple of 17 that has a 4 as a unit digit, and that is just 17 times 2, which is 34. And then we just add 170s, right? To keep the unit digit of 4. So listing out the first 3, we have this. Now, one thing we can notice is we have 209 and 204, right? And these are very close. These only differ by 5, right? And if you think about it, our units digits are 9 and 4, right? So the smallest possible absolute value between these two numbers has to be 5, right? Because the unit digits are already 5 apart. There's literally no way you can have it smaller than that. So which means here we already have our least possible absolute value difference. So then we just multiply this by 7, then we get 35. So this should be our answer. Whoops. Yeah, that's your answer. Don't look there, by the way, if you don't want to see the answer to 5. Yeah. Um, so not that bad, but really we just got pretty lucky with this one. Um, Bill, what do you think we should do, like, if we didn't get that if we didn't
What do you
get
mean
so
we
lucky here.
didn't get that?
If we listed the first few out and we didn't get like a difference of 5.
Oh,
I mean, yeah, you can guess
you can
5,
definitely
but
guess five. That's like a safe guess, I would say. Um, I don't think I
hmm.
actually when I was doing this because I was the one that basically found out that if you list them out, you get a five. I think when I was doing it, I was just trying to list them and then see if like their differences form a pattern. I think that was what I was trying to do. Like I would list them and see if their difference like have a distinguishable pattern.
I mean, I think I don't know. This is kind of janky, but just think about like these numbers like just go on forever, right? Um, they go on forever. They should converge to the smallest possible absolute difference at some point. Um, maybe we could reason through it. Um, so this sequence is going to be added by 110 every time, and this sequence is going to be added by 170 every time, right? So basically, we want the we want the digits after the unit digits to be the same, right? So then we just have like it's an arithmetic sequence with the not the unit digits, right? Like it's like we start with 9 and then we have what 20, and this is an arithmetic sequence by 11, right? And then this is an arithmetic sequence starting with 3 and it goes to 20 and it goes to 37. This is plus 17, right? But let's say these didn't equal, right? Um, but like if you add these have to equal at some point, right? Um, yeah, they have to equal at some point. Um, the only way they would not equal at some point is if they were multiples of each other, right? Um, I'm still thinking about it, kind of. Yeah, I think. Uh, no, okay. It's like I think it's like if the two numbers have a or if the two numbers are not relatively prime, then they might not converge. So like if we had +4 and +6, see we could have +6 as so these are not multiples of each other, right? They're not like factors of each other. So the +6 we can have like 6, 12, 18, and so on, right? But for the 4, we can just have it as 1, just always on the odd numbers, and there's no way they could equal each other. So why does this happen? This happens because 4 has a common factor with 6, right? But if they were not relatively prime, it would make sense that they would have to converge at some point. Um, I mean, it's like this, right? We could look, or uh, okay, yeah. So we could look at this sequence mod 11, right? Perhaps. Uh, yeah, sure. We could look at this sequence mod 11. So then the all of these numbers would be the same mod 11, right? So in this case, it's all 9 mod 11. So all of these numbers are the same mod 11, right? And they encompass all of the 9 mod 11 numbers, right? So basically, we're just looking whenever 17, this plus 17 sequence hits 9 mod 11. Now, there's probably a specific theorem for this. I don't know what its name is though, but that's if you have this sequence, it's it's increasing by 17, then the mod of another number, which is relatively prime to this number, then all the numbers in the sequence will go through all of the possible mod 11 numbers, and it will do so in a sequence of period 11. Right? Does that make sense? Um, I think there is a theorem for this, but I totally forgot the name. Um, but yeah, that just makes sense in my head because they're relatively prime. As this goes through, it has to touch like all the numbers, like 1 through 11 mod 11. So yeah, so because it has to touch all of them, then at some point it's going to touch 9, or it's going to touch 9 infinitely, actually, right? It's going to touch 9 every period of 11 times. But yeah, so because it touches 9 at some point, it's going to equal it's going to equal one something in this sequence, right? And it's not just with 9. This can be anything, right? We said it goes through all of them. So because these two are relatively prime, they're going to have to equal at some point. So which means what? If they equal at some point, then the units which are just going to be have the difference of that. So yeah, then there we go. We just proved that it's going to have a difference of 5 at some point. Um, on the actual test, I don't think we should go that much in depth. So like on the real test, if I listed a few out and I saw that I didn't see like close ones so far, I might just go ahead and guess with 5, and then if I wanted to come back to this problem later and then think on it more. Um, Bill and I are both virtual. Anything you want to add on to this, Bill?
Um.
Do you know what that theorem is called? Like,
Oh no. I know you. I don't know the names of theorems, so that is not something I am very good at. The naming theorems. I just know the theorems. I don't remember the names of them,
but yeah,
but
that makes sense, right?
yeah, that makes sense. Yeah. But yeah, during the actual test, like definitely don't do this. Don't do this. Do not do this. Come on.
Yeah,
This is
unless you have bunches of time, but you probably won't because you should be working number 5 instead, right?
right.
Um, how's stuff going at Hutch? You're at Hutch right now, right, Ishan? I think Lubbock High is doing kind of bad. I don't know.
Kai is doing really bad.
How many cases are there?
Over 30 something, I think. I don't know. There's also like 100 something quarantine.
Oh yeah, there's like 100 something quarantine. Maybe it's like those people have symptoms, but like they haven't tested or something. I don't know. All right. Um, let's move on to number 7. We're getting pretty close to time, so let's say this is our last problem. Okay, so we actually don't get finished today. So next week we'll finish this. And then yeah, and then we'll see. Okay, two square tiles, each with sides of length 6 inches, are arranged so that one lies directly on top of the other. The top tile is then rotated counterclockwise about its center until one of the exposed corners of the bottom tile has height 1 inch as shown. What is the area of the shaded intersection of the two tiles? Express your answer as a decimal to the nearest 10. All right. So, okay. So by symmetry, we can see that this this side length will also be 1, right? And all these like small lengths will all be 1 inch. Um, so what can we do here? We could try labeling this like long leg as X and then see where we get to with that. So then, if I just roughly draw this here, then we have 1 inch here, X here. This is X squared plus 1 rooted. So the hypotenuse is always going to be root X squared plus 1. So this is going to be root X squared plus 1 as well. This will be X and this will be 1, and this will be 1, and this will be X. Okay, so we know the side length is 6, right? So then we can set up an equation with this, right? We could say 6 equals 1 plus root X squared plus 1 plus X. Wait, why do I have another one? Yeah, it should just be this. Because that's just the entire side, right? So then we have 5 minus x equals root x squared plus 1. And we can try solving this for x by getting rid of the radical, right? So square both sides. And we see that our x squares cancel, so that's nice. So then we just have 24 equals 10x. So then we have x equals 2.4, right? And we want to find the area of the shaded intersection. Well, what we can do is we can find the areas of these triangles and subtract it from the area of the square originally, right? And then that will give us the shaded area. So then that's going to be 36 minus 4 times the area of the individual triangles, which will be 1/2 times 2.4 times 1. So then this will be 36 minus 4.8. So then what is this? 31.2. And yeah, the answer is 31.2. Yeah, so not that bad. All we did was say the sine length of 1 was x, and they used the Pythagorean theorem, and then just related it to the side of 6 inches. All right, that's all we're gonna do for today. Also, what do you guys think we should move on to next? Like 2015 state or 2015 nationals? 2015 nationals, okay. And and okay, so maybe next week when we get done with the rest of the team, we can set like maybe 30 minutes or so and try to solve number 5. Yeah. Or maybe we can also talk about if any of you guys have solved it on your own. All right. So yeah, that's gonna be all for today. We'll do 2015 nationals next week as well. Um, do you have anything to say to this problem, Bill?
That problem? Um, 1001. Remember symmetry? Yeah, this is it. This is symmetry. No, why are you doing that? This is. Remember when we talked about symmetry? Yeah, this is also symmetry. This problem. So, yeah. All right, bye.
Oh yeah. If you don't have